Hello guys, let us today see few questions based on groups and subgroups. Here I have a questionnaire. Let us first handle question number 6. Let me read it out. Let capital H be a subgroup of a group G. For A, B belonging to G, we define tilde as let A tilde be if and only if A into B inverse belongs to H. Then show that tilde is an equivalence relation on G. So let us recall the meaning of what is an equivalence relation. So better we all know, if we are having a set X with us and we have a relation capital R on X, then we have to decide whether the relation is an equivalence relation or not. How do we do so? R must be reflexive. R must be reflexive means what? For every element of X, if A belongs to X, then A must be related to itself, means ordered pair AA must belong to R. This is the meaning of reflexivity. Secondly, R must be symmetric. Meaning, if I have two elements A and B from the set X, and we know that ordered pair AB belongs to R, this should imply that ordered pair BA also belongs to R. Ordered pair BA also belongs to R. And third thing, transitivity. So if suppose I have three elements A, B and C such that A, B, C are members of X, and what we know is A is related to B, means ordered pair AB belongs to R. Also I know that ordered pair BC belongs to R. This will imply ordered pair AC belongs to R. So we can see A related to B and B is related to C will mean A is related to C. This is the transitivity relation. Now we are handling a group G. G is a group. So this group may have subgroups. Now we select any two elements A and B from the group G. Then A is related to B, A tilde B. If and only if, when to say A tilde B, if and only if A into B inverse belongs to the same subgroup, belongs to some subgroup H, then we say that A is related to B. Alright, we want to show that this is nothing but an equivalence relation. So let us go one by one. Very first, let us check reflexivity. So we have taken A from G. So A has to belong to some subgroup H. Yes. And for A, I know if I operate A to its own inverse, It produces an identity element, and identity element is always present in a subgroup. Identity always belongs to H. So no need of searching for A from which subgroup I have taken. A into A inverse belongs to a subgroup. Will mean that A tilde A means tilde is reflexive relation. Reflexivity is obeyed. Now let us go for second, that is symmetry. Suppose A comma B we have taken from G, and we know that A tilde B. A tilde B itself means that A into B inverse belongs to a subgroup H. So A into B inverse is an element which is a member of H. But we know that H is a subgroup, means H itself is a group. Will mean that the inverse of this element is also in H. So A into B inverse, inverse. By the reversal law, it is nothing but B inverse, inverse into A inverse, reversal law. And this is nothing but B into A inverse belongs to H. So what this gives us, B into A inverse belongs to H means B tilde A. So what we understood, tilde is symmetric also. Tilde is symmetric also. It obeys symmetry. Now let us go to the third one, that is transitivity. So I need to go for transitivity now. So let us take three elements A, B, C from the set G, and suppose A tilde B, comma B tilde C. First related to the second and second related to the third. This kind of thing we have assumed. So what this means, A into B inverse is a member of H. Same way, B into C inverse is a member of H. H being a subgroup, I can operate the elements, and I know by binariness AB inverse into BC inverse has to be in H. It's a member of H. I can say it belongs to H. It belongs to H. So let me simplify it further. So what I'll do is, I'll just go on applying associativity. So what do I have? This will be bracket AB inverse, and by the use of associativity, I'll be getting B over here and into C inverse as usual. Again let me apply associativity. So what this will produce? In bracket, I do have A into B inverse B, and outside I have C inverse. What is this equal to? A as it is. B inverse B is E, so I got A into E times C inverse, but A into E is A itself, and this value is C inverse, and already we have seen it's a member of H. So AC inverse belongs to H means what? A tilde C. Thus tilde is transitive. So we have shown that tilde is transitive also, it obeys transitivity, and because tilde obeys reflexivity, symmetry and transitivity, therefore tilde is an equivalence relation on the G. Tilde is an equivalence relation